Hi everyone, my name is Prasant Yadav and we have done a group project of EV dashboard and ADAS using STM32 Bluepill and Pixim Lab and Python. We are the group of the three students Prashant Yadav, Aman Baghel and Ankit Banwal. Now let's move to the problem statement. Modern EV needs fast, reliable monitoring for speed, battery states, monitor temperature, and near obstacles. Our project tracks four core challenges: accurate speed and dynamic tracking, continuous battery and state of charge estimation, thermal management for a motor, and a low latency obstacle awareness for a driver assistance. Project objectives. Our project were fivefold: simulate complete EV operation inside Pixim Lab, monitor real-time parameters like speed, SOC, torque, and temperature, implement core ADAS safety features, build a live Python dashboard, and essential relatable URT communication between the embedded system and the host. Now further we move to the system architecture. Our system work in four simple steps: sensor collect real world data, the STM32 board process the data instantly, then it send the data to the computer, and finally Python show it all on real dashboard. Hardware components. For hardware, all simulated in Pixim Lab were used the STM32 Bluepill as our main controller. We use ultrasonic sensor on the front, left and right side of the detect obstacles. We use nodes called potentiometer to act like the accelerator, brake, battery, and temperature control. We use LED to show warning light. Software stacks. Our software tools include STM32 Cube IDE to write the framework, PiximLab to simulate the hardware, and Python to read the data, plot it, and show it on our dashboard. Now move to the EV parameter calculation. We calculate speed using wheel signal and precise timing. We track battery charge by measuring current and voltage together. We calculate torque from the motor current, and we track motor temperature using a simple heat model. All of these also power our driving model Eco, Normal and Sport. Now move to the ADAS feature. For driver safety, we build three main features: front console, front collision warning alert the driver based on distance and speed, build stop detection use side sensor to catch nearby objects, and time to collision work out how many seconds are left before a possible crash and warn the driver in time. Now move to the fault detection and alarm system. Our system keeps checking itself for problem, sensor error, data error, or missing signal. We sort these into three levels: critical issues stop the vehicle right away, warning alert and driver, and minor issues just get logged for later. Each level has its own light and dashboard alert. Now let's further move to the URT communication and telemetry. All our data travel over a fast serial link in a small organized pack. Each pack has a header, a number of keep things in order, the actual data, and the check code of catch error. This way our Python program can check every pack and error anything that broke. Now Python dashboard overview. Our dashboard shows everything in one place: a live speedometer, a battery indicator, and a speed history graph. Key number like voltage and range, a bird's eye view for nearby obstacles, and a list of active alerts. Now complete data flow. From start to finish, data moves through four stages: sensing, processing, sending, and finally showing up all on the screen. This flow helps us test and fix the whole system easily. Demo workflow. Here's how our demo works. We start PiximLab, adjust the sensor value to act like real driving conditions. Let the STM32 process that data, send it over to the computer, and watch. The dashboard update instantly with warning popping up the moment something gets too close. Code architecture. Our code is organized into clear sentence. The fireware handles sensor communication and safety logic separately. And on the computer side, Python is split into three simple parts: read the data, understand it, and updating the screen. Challenges faced. Along the way, we face a few challenges: keeping the data packets lined up correctly, calibrating our sensor, keeping the graph smooth, building a strong data radar, and using debugging tools to test everything properly. Future improvement. In the future, we like to add real vehicle network support, GPS tracking, and real sensor instead of simulated one. A touchscreen dashboard, cloud connection, a mobile app, better data logging, and even AI powered safety feature.
Hi everyone, my name is Ankit Vanwal and I am presenting my course presentation, that is EV dashboard with ADAS using STM32 Blue Pill. Now the project outcomes. The project successfully demonstrated the integration of embedded hardware communication protocol and desktop software into one complete system. It validates real-time EV parameters, monitoring ADAS implementation, UART-based telemetry, transmission and Python-based visualization. The project also demonstrates how multiple technologies can work together to create an efficient monitoring system. Overall, the project provides a strong foundation for understanding embedded automation application. Key learnings from this project. Throughout the project, I get hands-on experience in several important areas of embedded system engineering. This includes STM32 programming, firmware development, firmware configuration, embedded C programming, UART communication, Python application development. I also learned how to visualize live embedded data using graphs and dashboard components as well. How to organize software into modular components for maintainability. Most importantly, the project improved my understanding of complete embedded system integration from sensor acquisition to real-time visualization. Conclusion of the project. In conclusion, this project successfully simulated an electric vehicle dashboard integrated with basic advanced driver assistance system feature. The STM32 Blue Pill process simulated sensor data, provides EV and ADAS calculation, and with sensor communicates with a Python dashboard through UART. The dashboard provides a clear and intuitive visualization of all important vehicle parameters, which also displaying safety warnings and fault information in real time. The project demonstrates complete embedded development workflow, including sensing, processing, communication, and visualization, and serve as a solid foundation for future automotive and embedded system projects. In the end, I would like to thank you for everyone time and attention. Throughout this project, I was able to design and implement complete embedded system that combine STM32 firmware development, sensor simulation, UART communication, and a real-time Python dashboard in one integrated solution. Although this project was developed in a simulated environment using PixSimLab. It demonstrates the same workflow followed in many real embedded automated systems, from acquiring sensor data, processing it inside a microcontroller, communication, communicating through a serial interface, and finally presenting meaningful information to the user through an interactive dashboard. This project has significantly improved my understanding of embedded programming, peripheral interfacing, real-time communication, and system integration. It has also given me a practical experience in designing both firmware and the visualization software that work together as a complete application. Once again, thank you for listening to my presentation, and I like to express my sincere gratitude to EMERTXE Information Technologies for providing me with this valuable internship opportunity. Throughout this internship, I gained practical exposure to the embedded system development and learned concepts that go beyond classroom knowledge. The structured training and hands-on project experience have significantly improved my technical skills. Now I'm gonna show you the simulation through the Pixim lab that we have done during the entire internship. As you can see that this is the Pixim lab. These are the three ultrasonic sensors. These are the status LED, and this is the simulation for acceleration, brake pedal, SOC, and motor temperature. This is a fault indicator version which beeps if there is any fault. Here is the virtual terminal, and you can see the values are popping here every like 2 seconds, because you can see here associate temperature here, front distance, left distance, time to collisions, alarms and flags. And you can see that these will change as I change the values. Just a second. See, as I change the distance of the front, uh, the first LED, the red LED is glowing, and sometimes it beeps accordingly, and also left distance and all the parameter here can be reflected. Let me fix this 1 second. Okay, as you can see the distance things are working. Now let's check the SOC first. See, as SOC drops, the yellow light clearly turned on. As I increase the pedal, here you can see the pedal is brake pedal is also updating. This is the complete walkthrough of the simulation. As I change the values in here, also we can see in the virtual terminal. Next we will see the Python dashboard. Now I'm gonna show you the Python dashboard working code. The Python dashboard is made using Matplotlib, NumPy, and Kinter for GUI. Matplotlib is used for the graphs, and the other things. At first, we import all the required modules. These include serial for UART, communication, threading for background data recording, regular expression for passing incoming data, Matplotlib for creating the dashboard. The next section is share data. This acts as central storage where all the latest vehicle parameters such as speed, battery percentage, obstacle distance, and fault status are maintained. Every part of dashboard reads values from this share state. After that comes the pass one UART line section. This function receives the telemetry data from the STM32 and extract all the required values using regular expression. Once the values are extracted, they are stored in the shared state. The next section is the serial reader thread. This continuously listens to the serial port in the background. Whenever new data arrives, it calls the parser and updates the dashboard without blocking the user interface. Next, the dashboard layout section. creates the main window, divides it into different panels for speedometer, battery information, speed history, EV matrix, and the ADAS board eye view. The following section contain individual drawing function. Each function is responsible for drawing one component of the dashboard, such as the speedometer, battery indicator, and the trend graph, information panel, or ADAS visualization. The animation update section refreshes all these components every 100 milliseconds using the latest value stored in the shared state.
Hello everyone, my friend has already covered the code part and the previous slides. Now let's move forward towards the EV ADAS dashboard. As you can see in the video, at the center we can see the speedometer which displays the current speed of the vehicle. Just below it, the speed history graph shows how the speed has increased or decreased over the time, helping us understand the vehicle driving pattern. And now at the top, we can see the battery percentage, which indicates the remaining battery charge. As the vehicle runs, the value gradually decreases. Below that is the EV matrix section. It displays important information such as driving mode, motor torque, accelerator and brake input, fault status and motor temperature. These values help us monitoring the health and performance of the electric vehicle and quickly identify if any issue occurs. And now let's move to right side of the video. In the right, you can see the section shows the ADAS bird eye view, which improves driving safety by monitoring the area around the vehicle. The system continuously detects nearby obstacle and measures the distance between the vehicle and the object. It also calculates the TTS called time to collision, which estimate how soon the vehicle could collide with the obstacle if it continue at the same speed. When the obstacle come too close and the TTC becomes very low and the dashboard immediately display an advisory warning to alert the driver. This gives the driver enough time to slow down or change direction to avoid the collision. Once the obstacle is no longer in the danger zone, the warning automatically disappears and the system return to normal.
Thank you for your time and attention. I hope this presentation clearly demonstrated the design and implementation of my EV dashboard with ADAS project.